Let us explore the fundamentals of binary search. It is an efficient algorithm designed for locating elements within sorted arrays. Binary search is an efficient search algorithm specifically designed for sorted arrays. At each step, it divides the search space in half, focusing on the portion that may contain the target value. It achieves this by comparing the target value with the middle element of the search space. The time complexity of binary search is O of log n, making it significantly faster than linear search for large datasets. Before applying binary search, there are key requirements that need to be met. First, the array must be sorted in ascending or descending order. Second, random access to elements should be possible in constant time, denoted as O of 1. Third, the elements must be comparable, meaning we can determine their order relative to each other. Finally, the collection of elements should have a fixed size. Here's an example in Python to illustrate a sorted array with numbers 2, 5, 8, 12, 16, 23, 38, 56, 72, and 91. Binary search operates through a series of steps to efficiently find a target value within a sorted array. First, a left pointer is set to the index of the first element, and a right pointer is set to the index of the last element. Next, we find the middle element located between the left and right pointers. If the middle element matches the target value, its position is returned. If the target is greater than the middle element, the left pointer is moved to mid plus 1, thus ignoring the left half of the array. If the target is less than the middle element, the right pointer is moved to mid minus 1, thus ignoring the right half of the array. These steps are repeated until the target is found or the search space is exhausted. Here's the binary search algorithm implemented in Python. Initially, set the left pointer to 0 and the right pointer to the length of the array minus 1. Enter a while loop that continues as long as the left pointer is less than or equal to the right pointer. Inside the loop, find the middle element by taking the integer division of the sum of the left and right pointers by 2. If the middle element equals the target, return the middle index. If the middle element is less than the target, update the left pointer to mid plus 1, effectively discarding the left half. Otherwise, update the right pointer to mid minus 1, discarding the right half. If the target is not found, return -1 to indicate that the target is not in the array. This algorithm achieves a time complexity of O of log n, as illustrated by the graph comparing it with linear search. Binary search boasts an impressive time complexity of O of log n, making it highly efficient for large datasets. The space complexity is O of 1 for the iterative approach and O of log n for the recursive approach due to the call stack. Each iteration effectively halves the search space, requiring at most the floor of log base 2 of n plus 1 iterations. Consider the following table comparing linear and binary search. For an array size of 10, linear search may take up to 10 steps, while binary search takes only 4. For 100 elements, linear search may take up to 100 steps, while binary search takes just 7. As the array size increases to 1,000, linear search requires up to 1,000 steps, while binary search only requires 10. For 1 million elements, linear search may take 1 million steps, while binary search is completed in just 20. Finally, for 1 billion elements, linear search may take up to 1 billion steps, while binary search is completed in 30 steps. Binary search is applied in various scenarios because of its efficiency and speed. One common use case is dictionary lookup. It enables fast word searches in dictionaries and spell checkers by quickly finding words in sorted lists. Secondly, database queries are also optimized by binary search to quickly locate records by enabling efficient searching through large datasets. It powers IP routing tables and search engines, ensuring fast data retrieval in large-scale network infrastructure. Finally, it is also used in game development in collision detection, pathfinding algorithms, and AI decision trees for efficient in-game calculations. In summary, binary search offers several strengths. It is dramatically faster than linear search for large datasets. its logarithmic time complexity O of log n ensures efficient performance. It has minimal space requirements when implemented iteratively. It also provides a predictable worst-case performance and serves as a foundation for more complex search algorithms. However, binary search also has limitations. It requires the data to be sorted. It is not efficient for small datasets. It needs random access, making it suitable for arrays but not linked lists. The initial sorting step may offset the performance gains, and it is not ideal for frequently changing collections. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.